is Akshita. In today's video, I am going to cover the topic circuit models of power system components. So we know that in power system, a power system mainly consists of generating station, transmission line and distribution system. So when you have a modeling or when you are going to do a power system analysis, you need to understand before that what is symmetrical system and what is a balanced system. Okay, so symmetrical system is, so when you're considering a three-phase, okay, so this could be a generator or transmission line or a load. So when you're going to consider this, the impedance, that is Z of phase A, and this is Z of phase B, and this is Z of phase C. So all these impedances of A, B, C, that is ZA should be equal to ZB, which should be equal to ZC. So it means that when you view from any of the phase, all the impedances must be same. So in case there is any mutual impedance existing between any of the phase, then the same value must be existing between A and C as well as A and B. So then you tell that the system is symmetrical. So what is a balanced system? So balanced system is when a voltage of phase A and voltage of phase B as well as C are equal in magnitude, and currents of phase A, phase B, phase A and phase B and phase C is equal, and the second condition is the phase angle difference should be equal. So if you are considering a three-phase, obviously 360 divided by 3 is 120 degree. So the phase angle difference between the phases will be, you can see here, if I consider the phase sequence A, B, C, then this is IA, IB, IC, or it could be VA, VB, VC. The phase angle difference between each other is 120 degree. So these are the two conditions for balanced system. So now, for a large power system components, there are actually many generators, all with three phases. Okay. So now here, all the generators will be having three phases, and then step-up transformer, step-down transformer, transmission line, and then finally to the load, distribution system and load. So now, when you are considering all the power system components with the three phase, considering the reactance values of each, it is very difficult or very complicated to analyze the whole power system. So that is the reason why this needs to be simplified to analyze the complicated system. So that we have circuit models or single phase equivalent diagram. So single phase equivalent diagram is applied only for symmetrical balanced system. That is, if a system is having the same impedances and same values of currents and voltages. So for example, if I am considering this generator, so the single phase equivalent value is just taking only one of the phase of generator, because all the three phases are same, taking only one of the phase. So I am considering only one of the phase of generator. Okay, this could be phase A, B or C, because all the three are same here. So let me just consider any one of the phase. So now this is nothing but single phase equivalent diagram. The purpose of analyzing the system is, the first one is planning the operation. So whenever a new operation must be planned, so then you must analyze the complete system and accordingly you must plan. And the second one is you need an improvement in the system. Then again find out all the ratings or load analysis or short circuit analysis. For all of these things, the power system analysis or modeling has to be conducted. And the third one is expansion of the system. So next is equivalent circuit of two-winding transformer. So when you are considering a two-winding transformer, either you must refer the primary side or refer the secondary side and draw the equivalent circuit. So first let me draw the circuit of the two winding transformer. So this is the primary side. So we know that how do we represent usually the two winding transformer. So I'm going to represent the primary side, which you represent in this way. And next you have the secondary side here with N2 number of turns. Okay. Now, when you see here, there are two separate coils. It's not a single circuit, but when we are doing the analysis, we should have a single circuit. So that is why I told you in the beginning to refer either to primary side or secondary side. So it means that you are shifting the impedance of the secondary side to primary side and then sorting out a primary. So if you are telling that you are referring the secondary side, so it means that you are shifting all the values of primary to secondary. So when you are shifting that, you need to consider the transform ratio, that is the ratio of N2 by N1 value. So now if you check in here, the primary value, that is R1 X1, and this is the exciting circuit, that is R0 X0 with a current of I0, and this is primary current I1. So now I am shifting the secondary values to primary. So this value is R2 dash, and then you have a reactance, that is X2 dash. So this is the secondary side voltage V2 dash. Now you might have observed all the values are in dash. I have represented not R2 but R2 dash. So why is it this? When I am shifting the value from secondary to primary, the values get changed. So that is, the value of R2 is nothing but R2 by K square, and the value of X2 is X2 divided by K square. So this is I2 dash. So now this K value is nothing but transform ratio, which is nothing but N2 divided by N1 or V2 divided by V1 or I1 is equal to I1 divided by I2. Equivalent circuit of a transmission line. So we usually represent in nominal pi method. So I am going to draw the scene. This is the impedance of the transmission line, and this is half line charging admittance. On either sides, and this is the sending in voltage and sending in current, and this is the receiving end voltage and receiving end current. So this is the equivalent circuit of transmission line. Equivalent circuit of a 3-winding transformer. Basically, why do we use this 3-winding transformer is, using 2-winding transformer, the primary side and secondary side kVA ratings will be same, but the same is not in case of 3-winding transformer, because all the 3 windings have different kVA ratings. Let me just represent the symbol of 3-winding transformer. This is primary, secondary, and this is tertiary. So if you are writing the equivalent diagram, this is ZT, ZT, and this is ZS. So P, and S. ZPS is equal to, so this is nothing but the leakage impedance with secondary short circuited and tertiary open. So this is P to S, the impedance, so ZP plus ZS. Next is ZPT. So here tertiary short circuited and the secondary is open. So ZT plus ZT, and next is ZSC. So here the primary is open and tertiary is short circuited. So ZS plus ZP. So if you are considering this as equation 1, 2 and 3, adding 1 and 2 and subtracting it with 3, that is ZPS plus ZPT minus ZST. So now when you are adding this with this and subtracting here, so ZS and ZT will get cancelled with this. So ZP plus ZP becomes 2ZP, so 2ZP. So now we can find out the value of ZP. So ZP is nothing but ZPS plus ZPT minus ZST divided by 2. So similarly you can get the equation for ZS as well as ZP. So ZS is ZPS plus ZST. So ZPS plus ZST and then minus ZPT divided by 2. So for this you need to add equation 2 and 3 and subtract it with equation 1. So next is ZT. So ZT is ZPT plus ZST minus ZPS divided by 2. So adding the equation 3 and 1 and subtracting it with equation 2. Okay, the advantages of 3-winding transformer are, so these are used for interconnecting 3 transmission lines, each working at different voltage and power levels. Find extensive utilization for high voltage laboratories. Static condensers may be connected for tertiary for reactive power injection. Next is equivalent circuit of a dynamic load. So dynamic loads are basically the synchronous motors and induction motors. So synchronous motors we have already discussed in the beginning. So let me just discuss on induction motor. So in the induction motor, you have stator. So this is the stator side, and then the magnetizing circuit, and then this is the current in the stator and voltage in the stator, voltage supplied to the stator, and then the resistance of rotor. So again I am mentioning this, it is similar to the one what you have studied in the transformer. So transformer secondary we have shifted to primary, with respect to the primary side we have written there. Same way here the stator, that is rotor side, we are shifting it to, we are writing this with reference to stator side. So we have shifted the values of R. So we are going to write it as RR divided by K square. Same way this is XR dash, which is nothing but XR divided by K square. And the variable load here, sorry, RR divided by K square into 1 minus S divided by S. So this is the variable load. So this is the single phase equivalent circuit of the dynamic load. Equivalent circuit of a static load. So electric furnaces, lamps, etc. are the static loads in the power system. So you just have to represent it with the impedance of the load. So this is the single phase equivalent diagram of the load.